Okay, I've got, a Hantek 1008b, 8-channel engine analyzer, but I'm actually not using it for engine analysis. I'm using it for, a cheap 8-channel scope, and I'm still not really sure about what the performance of it actually is yet. I think it's like 2.5 megasample. I don't know if that's per channel or overall, but but it does have, like I said, a lot of um, connections, BNC connections on this side, and then a couple on that side. But channel one here is at the top, and then it works its way down. Right now, I'm only using 4 of the channels, but I got this JD 6600 function generator, which I actually love this damn thing. I swear to God, I wish I would have had one of these a long time ago. But anyway, I'm generating, a 10 kilohertz signal, as you can see on that particular channel, and then on channel 2, I'm generating a sine wave. Although I guess it doesn't show you a picture of that. I'm still learning to use some of these things. But yeah, I'm just generating a sine wave on channel 2 at the same frequency. About 10 kilohertz. And feeding it into these channels. And you can see the scope here. Let me try to get this expanded here. So you can see that I've got it set to 10 seconds per division, and here is the channel 1 frequency, which I think is the only thing, and again, I'm still learning how to use this thing too. I'm trying to determine if I want to keep it or not, but it's measuring 208 millihertz. But you can see the waveform is accurate, and the point of this video is to show you the pitfalls of aliasing, particularly on, cheap scopes. So, this thing apparently does change its sampling rate, significantly with your frequency setting here, which doesn't surprise me. It's kind of similar to a little piece of test equipment I built over there, which does the same thing, just not at as high a frequency. It's an 8-channel too, but it was a great example of Nyquist and how even at fractional frequencies, you can generate phantom signals. These are both phantom signals, but yet they keep the characteristic of a pure sine wave and of this, even though it thinks it's only like 200 millihertz. When it's a 10 kilohertz, both of these are 10 kilohertz signals. In fact, this up here is a 430 hertz or so square wave that's coming from that little 555 generator, and the other signal is coming from this little probe, which is not amplified, but it's a little electric field probe, which is very interesting. It's actually pretty sensitive, but I got it like laying next to that thing, so it's actually triggering at the same rate the square wave is, more or less. But again, and this red squiggly thing is the FFT. I can't even. I think I've got that tuned to the pink signal there. But anyway, the point is that you got aliasing effects here that can show you on some of these cheap scopes a signal that really isn't there. I mean, it's the same exact waveform. Just like this is actually not the same waveform, because it should be synchronized with a square wave, but these are too high frequency for it. Because again, this is set to 10 seconds per division, so this right here, the square here is like 10 seconds wide, so it's acting like it's like there's like less than about two signals, 2 pulses per 10 seconds, so like 5 seconds a signal. So I mean a wavelength of about 5 seconds, or not wavelengths, but I mean a period of about 5 seconds. But let's see what happens though as we adjust the frequency. That's down to 5 seconds, 2 seconds. Now let's see, this thing has to get a full screen worth before it'll update the frequency. But again, so you're seeing this interesting frequency here. which again is a result of aliasing. That's interesting. I haven't seen that effect before. So, but yeah, now it thinks that it's at 1.38 hertz. So, but it still looks the same basically, except for this, which is, doing some weird shit. But again, this is all due to aliasing too. I mean, it's just a question. This shows that there's some jitter in the frequency, and there is some slight variations in the frequency from time to time. That's why you're seeing this little artifact here. It just happens to be picking up on that. But that's why we're getting these gaps here. So, they're not real though. They're not real gaps. So let's go ahead and, that's 2 seconds per division. Let's go to 1 second per division. Okay, so those gaps disappear, but still the frequencies look, still proper, and these two waveforms, the sine wave and our little waveform there. So I'm going to go down to 1/2 second per division, 200 milliseconds per division. Now it thinks it's at 19 hertz. Remember, it's measuring this yellow waveform here. I think that's the only, my impression is that channel 1 is the only one you can actually measure things like frequency with, but I'm not totally sure of that, but because again, I haven't gone through this whole thing yet. But now we're at 100 milliseconds per division. Now let's do 50, 20, and say at 20, okay, you start losing your characteristic, So, but this is actually starting to show signs of being, the 400 hertz signal it is. And you can start telling that because as you decrease the range, if you see the pulse start to change, get wider and wider, then you're seeing the real signal. So that square wave, we know we're seeing the actual square wave, but look what these other fucking things are doing. I mean, they're just going nuts. But because right now, as I change the time base, we're going back the other way with it. You can still see it, even here, that's probably the real signal. And this might be, but it's harder to say. 100 millisecond, it's, you really can't resolve anything or discern anything. But at any rate, see, we got it at 5 kilohertz now on this signal down here. Well, that's, getting close. Okay, now it's finally giving us a real reading of 10 kilohertz on the frequency. That's at 1 millisecond per division. So, so that's, kind of what you would expect. So what, 500 microseconds, 200, and 100 microseconds. So at 100 microseconds per division, yeah, that's what you would expect. You'd expect to see one pulse per, 100 microseconds. So, we're seeing the real waveform, and as I still increase it further still, you can see it starting to grow. So that means we're seeing the real signal now, not some phantom signal. So, but I mean, this is kind of cool in the sense that, yeah, you can go up to like 20,000 seconds per division. So, again, one of the reasons I bought this was for data logging purposes, but I'm a little nervous that, okay, well, if you had some occasional high frequency stuff, it'll show up as a phantom signal. I mean, the lower you set it, because it'll alias, I promise you, across all these waveforms. But it takes forever, when you get down to levels like this. I mean, you'll sit here and wait for, probably an hour for a data point to be logged. At 20,000 seconds, and like I said, even at 10 seconds, it's, it takes quite a while to do its thing, but you're seeing a signal that's not there. And apparently, let's see, this can go up to what the hell? I mean, it's hard for me to see this, because that's 1 microsecond right there. So, that's certainly way up there. at 1 microsecond per division. But it can supposedly go down to 1 nanosecond, I guess. I don't know how it would actually accurately resolve any of that if it's 2.5 megasample. But going back to 10 microseconds, 100 microseconds, per division, that's where we're at. Going the other way, 50 microseconds. But, this is making me wonder, okay, if you use it as a data logger and you're worried about some occasional sporadic frequency on your channels, you're going to have to sample it at a much higher rate than you might want to. I mean, you might just be sampling a signal, that's like a couple of hertz or something, if that. But because of the aliasing problem, if there's some signals that are outside of that range, you're going to have to really sample a lot. If it's like, let's say there's a 2 hertz signal, well, you'll probably want to sample it like 100 times that, okay, just to make sure. So that's a lot more data you're going to generate. And I'm still not sure if this is capable of recording that much data or not. It should. It's on a PC. But I still haven't even figured out exactly how that works, because, you got this recorder thing, and I'm not sure if that's just recording video or not. But there is a data thing, but I'm not sure what you're dumping on that. Like I said, it says save as, all, and you can choose the channels individually if you want to, and then name it, and I'll name it 2. Okay, so let's see how big that is. I think it's here. Let's see, that's only 5 kilobytes, so I mean, that didn't save much data. So, so this one I did a while back, saved a lot more. I don't know how this works yet, so again, that's still something I'm wondering about. But let's see what happens, when we change this to, change the frequency here. Let's see. Oh, no, wrong channel, damn it. Change the frequency here. I think I changed that to 11 kilohertz. Shit, let me change that back. Well, I think I changed it to 1 kilohertz. Yep. Okay, change that back to 10 kilohertz. Alright. Now, let me go over this. Let me go this way. Change it to 100 kilohertz. Alright, so, okay, you can see this thing now, is not resolving that signal very well. So, let's see, I mean, this is terrible. It certainly can't do a 100 kilohertz signal, that's for sure, but that's, according to the videos I've seen, that was about right. So, but yeah, you're not able to resolve, 100 kilohertz even on this thing. So again, it makes me wonder, well, let me see here. Because like I said, I've got like only 4 channels turned on. You got to go through here and individually turn them on. But let me see what happens when I turn these other channels on. I want to see if this gets worse, because this will tell me whether it's sharing an ADC or not with all channels, and I think it is. Yeah, because I mean, see, the resolution seems to get worse the more channels I turn on. So that, I mean, I'm not sure if that's what I'm seeing or not, but it looks like it is. But let me start turning channels off and turn them all off except for channel 1, and let's see if the resolution of this signal increases. Channel 4, channel 3, channel 2. Okay, so it's everything except channel 2, and yeah, the resolution has increased, but it's still not really usable. So, but yeah, so it's the 2.5 megasamples shared amongst all these 8 channels apparently. So that's what we're dealing with. So I don't know, about that, but let's change the frequency back down to let's go to 20 kilohertz and see what that looks like. Okay. Now we're getting, 20 kilohertz, we're getting a pretty decent looking signal. A little jittery, but let's change it to 30. Okay. 30, yeah, you're starting to see some, trapezoidal sort of effects here. It's starting to look, like a lot of dots connected with lines. You're starting to see these little, you know, flat areas. Let's go to 40 kilohertz. So 40 kilohertz, yeah, a little worse. 50 kilohertz, 60 kilohertz, 70, 80, 90, 100, 110. That's what 200 kilohertz looks like. At some point, I guarantee it'll start acting funnier and funnier. So anyway, yeah, this certainly can't even do 300 kilohertz for sure. And see, look at the frequency thing. It's saying it's 75 kilohertz. So let's see what happens when you reduce it. Okay. Okay, so at 240 kilohertz, it's saying it's 30 kilohertz. So 10 microseconds. Now it's at 50 kilohertz. I got it down to 220. So again, like I said, it's not really reducing down to 100, down to 40. So yeah, around, like I've seen in other videos and so forth, well, still it's saying channel 1 frequency is 7.5 kilohertz. I got it set at 30. See? So yeah, this thing, has some serious limitations if you want to use it as some kind of a general piece of test equipment. It's certainly not 500 hertz. Well, that's interesting. If I change the channel, that changes the frequency response. It's still saying channel 1 frequency. I don't know why it's saying that. I changed back to channel 1. Now it's registering the right frequency. So that's an interesting little bug. So now it's registering 30 kilohertz properly. So that's interesting. I guess that zoom thing does affect your measurement here. 40, 50 kilohertz, 66, 66. Now it's starting to. So it's going to. It's right. I got it at 80 kilohertz right now. It's measuring 75. So let's see what happens when I change the scale. It's having a difficult time with it. Let's see what happens if I change the voltage on it. No, it didn't improve anything. Still 75 kilohertz. I got it set at 100 kilohertz right now, and it's measuring 100 kilohertz, and it's the waveform is kind of recognizable, but it's pretty damn jittery. Um, but again, it's probably not something you'd want to use, but it's apparently, measuring the right basic frequency here. So, those settings. So, um, hmm. Now it's really confused what frequency it's at. 100 kilohertz. Yeah, it locks onto that pretty solidly. Let's go down to, okay, 90 kilohertz. It's saying it's 85. And 80 kilohertz, and it's 75. Again, it's acting jittery. The function generator is, from what I've observed, it's pretty stable. I think it's more the scope than the generator. Um, okay, I'm decreasing the frequency. We're down to 30 again. 30 kilohertz. So, I mean, it's certainly usable for sure up to 30 kilohertz at least. So, and again, here's 40, there's 50, so again, it could even be usable to 50 kilohertz. Maybe even 60 or 70, because that's why I chose this waveform, because it's a little more complex. So, even though this thing can generate a lot of other waveforms, I'm still learning to use this thing too. The function generator, that is. But at any rate, yeah, it's, but it does show you, how aliasing works and kind of what this, how this instrument works, because that's one of the questions I had. Was it 2.5 mega samples per channel, or was that shared on all channels? And apparently it is shared on all channels. So as I turn more and more channels back on, we're starting to, lose resolution on our signal. So basically, yeah, the more this does, the less capable it becomes. And see, it's, it's still, set at 40 kilohertz, and it's still occasionally saying it's 40 kilohertz, although it's sporadic. And channel 8. So, but again, yeah, it becomes certainly more undefined. Now I'll take it down to 30. And again, it's pretty scraggly. So, take it down to 20, 10. Now 10 is starting to be usable. So if you have all 8 channels, I would say 10 kilohertz at most. So, let's see. There's 9, there's 8, there's 7, 6, 5. So 5 kilohertz is starting to look, much better. 4, 3, 2, 1. Of course, 1 kilohertz it doesn't really have much of a problem with. Let's change this. Let's go the other way. Yeah, 1 kilohertz, so it's locked on pretty good. So, and this signal is still set at 10 kilohertz. Remember, I haven't adjusted that at all. So it's kind of showing you, what the useful range of this thing is. Again, I still have more to learn on this, and I'm still trying to make up my mind whether this is useful enough to keep or not, because it's like $100 oscilloscope. So, and again, I had a Tektronix 4-channel scope with 100 megahertz with DSO on it, but that thing just crapped out on me. So, I mean, it's like from the late 80s, but so I was kind of looking at, it's something that might be a cheap substitute for that. And, this is 8 channels instead of 4. And it's certainly a lot higher frequency than that. That's an Arduino-based version of this. But, again, its sampling rate's going to be maxed out. I can't remember. It's been a few years, but, like 40 kilohertz or something, and but its usable signal I think was like 5 or 10 kilohertz, you know. But again, it Nyquists out the ass just like this does, so I was rather disappointed to see that. So, at any rate, but this, you know, basically kind of, you know, shows you the pitfalls of Nyquist and this piece of equipment too. So, anyway.